Okay, hello. This is the homework video for Module 5, Equilibrium and Acid Reactions. This is homework 4. We're going to talk about solution equilibria with acid and base. This will be the final homework for Module 5 for chemistry. Okay, let's get into multiple choice. Question 1, which of the following is correct regarding to chemical equilibrium? Okay, so the right answer will be C. C says that a dynamic equilibrium is achieved when the forward reaction rate equals to the reverse reaction rate. Yeah, this is by definition what it is. Okay, it's kind of like a revision question. So B is wrong is because it says that static equilibrium is achieved when equilibrium quotient Q equals to equilibrium constant K. Uh, no, a static equilibrium doesn't have like meaningful K and therefore doesn't even have Q. Okay, a static equilibrium, we don't use equilibrium constant to quantify static equilibriums. Okay, A is wrong because it says static equilibrium is achieved when concentration of species become constant. This is not generally true. Okay. Uh, yeah. D is wrong because it says a dynamic equilibrium is achieved when reactants and product concentrations are equal. Not necessarily true. Okay. Question 2. The following reactions at dynamic equilibrium in a closed system. 4 is exothermic. You get that. The volume of the system is increased. Which of the following shows the correct effect to this change? So if the volume increased, the pressure has decreased. You want to shift the equilibrium so that you increase the pressure. Okay. So that means you want to produce more gas moles, right? By LCP, so you go towards the left. So equilibrium will shift to the left. Reason being that there are more gas on the left hand side. Okay. Right. Some revision questions. Question 3. Which of the following equilibria would be affected by volume changes at constant temperature? Okay, so it applies to gaseous particles, right? And for the first one, it is subjected to volume change because when volume change, there will be a change in pressure, and then because number of moles of gas from the reactant and products are different, you will get equilibrium shift. Uh, Reaction 2 has also um, different like moles of gas. On the left hand side, you have 9 gas. On the right hand side, you have 4 gas. Remember that water is in liquid form, so it does not have any pressure. Okay, that contributes to equilibrium shift as well. Whereas in reaction 3 has 2 gas on the left hand side and 2 gas on the right hand side. Changing temperature only affects the rate, but affects the rate equally for both directions. So it does not apply here. Okay, so this is why question 3 has answer to be A. Question 4. Which of the following shows the stages of dissolving an ionic compound in water in a likely sequence? Okay, so first of all, we have dissolution, right? So the ions separate, and then the solvent molecules separate, and then they recombine um, to form ionic dipole forces, which is the hydration of ions. Okay, and selection B directly matches that. Okay, sorry. Question 5. The correct expression for this solubility reaction um, is B. Okay, it's pretty straightforward. Okay, common mistakes is that either you mistakenly think solid has concentration and you will choose C instead, or the common mistake is that you have the factor of 2 instead of rising to the power, you will put it in front, which is also wrong. Okay, remember that stoichiometric ratio requires you to rise the equilibrium. When you write an equilibrium constant, the stoichiometric ratio is the power. Okay. Um, the molar solubility of magnesium hydroxide, we let that to be x moles per liter, meaning that 1 liter of water you can dissolve x mole of everything. Okay, which one of the following shows the correct expression of the solubility product KSP for magnesium hydroxide? Okay, so for this question, if you are fluent, you can just pick your answer, but if you're not, please feel free to write down the chemical reaction. Just showcase that the stoichiometric ratio. Okay, when it's saturated, you get a magnesium ion plus 2 hydroxide ions. Okay, so this will be x. This will be 2x. Okay, so the equilibrium KSP would be equals to x times by 2x to the power of 2. So that gives us D. Question 7. Which of the following substances would form a precipitate with sulfate ion? Yeah, solubility table is pretty straightforward. Or you guys can look at the formula sheet where it says the KSP tables, right? I believe that barium sulfate will be like on there. Okay. Right. Question 8. The equation shows the dissolution of silver chloride. Uh, okay, saturated solution of silver chloride. Which of the following statement is correct regarding to a saturated solution of silver chloride? So C, rate and forward reverse. That's basically because saturated solution means an equilibrium. Okay, dynamic equilibrium is established in saturated solution. A is wrong because the reaction has gone to completion. That's not true. We haven't gone to completion yet. Uh, B, a precipitate has not yet been formed as more ions can dissolve. That's not true. You could have ions dissolved and then precipitation as well simultaneously in a dynamic equilibrium system. D is wrong because the concentration of ion can be increased by adding that. This is not necessarily true. Adding more solid in a saturated solution does not increase the concentration because solid does not have any concentration, it doesn't shift equilibrium at all. Okay. Question 9. Which of the following metal carbonate has the highest molar solubility? Best this question, look on the formula sheet. Okay, look on the formula sheet and then um, get the KSPs. Now, because everything is like the same, like stoichiometric ratio. For example, calcium carbonate is CaCO3. Copper carbonate is also CuCO3. So when they dissolve, it's just like one by one, one to one, one anion and one cation. So you would calculate the solubility the same way. You always get x squared equals to KSP. So you will solve x in the same way. In that case, just compare KSP straight away. Okay, you end up having calcium carbonate having the highest KSP, meaning that it dissolves more, meaning that it has a larger molar solubility. So answer is A. Question 10. A saturated solution of barium carbonate was stored in a flask. Okay, so solid barium carbonate containing radioactive carbon 14 was added to the solution. The mixture was allowed to stand for several days. Okay, so it allows that because it's a dynamic equilibrium, right? So the solid radioactive source is allowed to redissolve, while the non-radioactive sources are allowed to reprecipitate. Eventually, they will form a dynamic equilibrium, and you will have some dissolved ions containing radioactive carbon. Okay, so therefore, it's both the residual and the filtrate. Okay. If there's any question towards the multiple choice, let me know and I'll carefully explain. All right, extended response. Okay, we begin with two revision questions. Hold on, let me just double check that this is the right booklet. Yeah, yeah. Okay. Yeah, for okay. Right, extended response. Extended response question 11. Consider the following reaction between dinitrogen tetroxide and nitrogen dioxide. An experiment was conducted with in which 0.1 moles of dinitrogen tetroxide was introduced into a 1 liter flask. After equilibrium has been established at 100 degrees Celsius, the concentration of that was this much. Okay, so clearly it's an IC table question. Okay, it was a revision from booklet 3. Calculates the equilibrium constant Keq for this reaction at this temperature. As temperature remains the same, Keq is the same. All right, so consider IC table. Okay, initially we have 0.1 mole of dinitrogen tetroxide. Be very careful that this is the number of moles, so you want to divide with the volume, although the volume is 1 liter, so it's kind of straightforward. Okay, so we would know that first, and then we know we have 0 of our product, but we know finally we have this much of our like reactant, so we know how much is being reduced for that, and then we can deduce how much is increased for that. Now be careful of the stoichiometric ratio, and using the equilibrium concentration, substitute into a KEQ equation. Okay, I don't know why I wrote KEP, but like you guys get the point. Right, yeah, that eventually becomes 0.211 into 3 sig figs. Okay. Question B. Use your calculated value for KEQ from part A. Calculate whether a mixture of 0.1 to 0 moles per liter of dinitrogen tetroxide and this much is at equilibrium. So the idea is we calculate the equilibrium quotient and compare it with the K value. If quotient is larger, then equilibrium is overshooted. So you want to shift towards the left in order to for Q to approach K. If the quotient is smaller than K, then you would shift to the right. Okay. So we calculated using the current given concentrations, we get a value of quotient equals to 2.52, which is much larger than the KQ value. As a result, dynamic equilibrium has not yet been established. The equilibrium will go towards the left in order for Q to approach K. Okay. Question 12. Magnesium phosphate has a solubility product of 1.04 times 10 to the power of negative 24 at 25 degrees Celsius. Write down a balanced chemical equation for the dissociation magnesium phosphate. Okay, it's pretty trivial. Just keep track of the molar ratios. Okay, guys, remember all the charges and all the valencies. Okay, at this point, you shouldn't need to look at the formula sheet and look at the location of the ions in order to figure the valency out. You should be able to just memorize it. Okay. If you still can't do that, spend some time, 20 minutes just to do that. Okay, it's very important. The language of chemistry is writing chemical equations. Okay, you have to be able to do that. Question B. Calculates the solubility in moles per liter of magnesium phosphate at 25 degrees Celsius. We always assume X mole of magnesium phosphate dissolves, okay, in 1 liter of water so that we don't have to keep track of the volume, okay. X moles dissolves, and then that produces 3 times X of magnesium ion and then 2 times of the phosphate ion. Substitute into your KSP equation. Be careful of the molar ratio and then the powers. You end up getting a degree 5 polynomial for X, okay, without any other lower order terms. Just simply solve for X, okay, with your KSP. You can get the KSP value from the formula sheet, okay. Or like it's given, okay, it's given the question. I'm pretty sure when I wrote this question, that number is the number I read from formula sheet, so it's the same thing. Okay, they could in the actuation C, they don't have to give you this number. Okay, you're supposed to just look it up for yourself. Okay. All right, question C. Using your answer from part B, calculate the greatest mass of magnesium phosphate that can be added to 100 ml water without forming a precipitate. Okay, so using the moles, right? Calculate the number of moles first. So this is what I did. So number of moles times by the molar mass. Okay, this is the concentration times by 0.1, which is that. Okay, and this is the molar mass. Right? Yeah, I'm getting this much grams. Okay, pretty much a year 11 calculation question. Pretty trivial. Okay, question 13. When some amount of sodium hydroxide is added to 100 ml of water, its temperature increases. So the reaction is represented by this reaction. The question gives you the reaction, but if the question didn't give you the reaction, please write it somewhere in your answer. Account for the temperature change by analyzing the process and in terms of enthalpy change, okay, involved in dissolution of that. Okay, so temperature increases. Okay, given the question, as temperature increases, this indicates that this whole reaction will be exothermic. So draw a little delta H smaller than 0 here for you. When sodium hydroxide is added to water, ionic bonds, so just describe that process, right? So ionic bonds between sodium and the hydroxide ion are first broken, and then the water molecules are therefore also separated away from their own hydrogen bonding, okay? And this process is breaking chemical bonds, so that requires energy input, okay? So it absorbs energy, a little bit energy from surrounding, and then subsequently, the ionic dipole forces start to merge between the ions and the water molecule, and this process is the establishment of new chemical relationship, which releases a lot of heat. Okay, now it just happens that when this bond are formed, you release more heat than the bond you absorb during the separation phases. Okay. So yeah, the total enthalpy end up to be exothermic because of that. Okay, this question could be like for students they could think this question is a bit vague in terms of like what do I answer? How do I know I have to talk about salt dissolution and the process of like ions and bonds forming and stuff? Okay, you just have to sort of get used to this kind of question. Yeah, when they ask about enthalpy changes, talk about the processes, right? Be very familiar with how salt actually dissolves or any compound actually dissolves. Okay. Right. And then question B, sodium hydroxide spontaneously dissolve at all temperatures. Okay, that's telling you the Gibbs free energy for this dissolution process is negative for all temperatures. Okay, based on this observation, identify the sign either plus or minus for the reaction entropy. Okay, delta S. So notice how sodium hydroxide dissolves spontaneously at all temperature. I give it straight away. Delta G must be always negative. Also consider the definition of Gibbs free energy using delta H and delta S. Write that equation down. We have concluded that the delta H for this certain reaction is smaller than 0. We need to ensure the fact that negative T times delta X is a number that's less than 0 to keep delta G less than 0 for all T. Okay. It's pretty much just the inequality expressions. Rearrange some algebra. You will get delta S being larger than 0 for all possible temperatures. Okay, so this dissolution process is actually increasing entropy, like what we expect, because we produce more ions than from a solid. Okay. Question 14. Using the solubility product value from the data sheet to determine the solubility in grams per liter, okay, of silver chloride. So we first determine the molar solubility. I see. So in my sample answer, I made the mistake because I didn't read the question carefully. Okay, we should convert the moles per liter concentration in terms of grams per liter. I'm gonna do that right now. Okay, so again, your context in grams per liter. What we're supposed to do is we use X in terms of moles per liter, and then we multiply that with the molar mass. Okay, so that is equals to 1.33 times 10 to the power of negative 5 into the molar mass. Molar mass for silver chloride, okay? Give me a sec. I need to check my formula sheet. So for silver, I think it's 107 something, yeah? Yeah, 107.9. And then for chloride is 35.5, 30.45, okay? Plus 0.45. Sorry about this, just give me a sec to calculate. Okay. It's not a big deal, just a unit conversion. I forget to do that when I write the sample answer. So I end up getting a 1.91. Okay, again, 3 sig figs, times 10 to the power of negative 3 grams per liter. Okay. Be messy, so I'll box the final answer. 3 sig figs. So yeah, this again highlights out how important it is to read the question carefully. Okay, don't make stupid mistakes like this. Question B. 1 grams of silver chloride is added to 18 liters of water and weighted. Okay. After the solution became saturated, it is filtered and the precipitate is then weighted. Using the result from part A, calculate the theoretical mass of the precipitate. Okay. So the idea is like we assume the 1 gram of silver chloride all dissolves in the 18 liters of water. Okay. And then we use that information, okay, to calculate the molar concentrations of silver and chloride if they're all dissolved. And then we're going to assume that X mole per liter of them precipitated out. And then we use IC table to figure out what X is, which is also the mass of precipitate, okay? So using the value I calculated above, forget to give unit. What's wrong with me? Moles per liter for that, okay? And then minus x is the precipitated, okay? And then we end up getting that. So by equilibrium constant definition, you just get that, okay? Squared equals to KSP and you take square root both sides. Or if you're nerdy, you could expand the bracket and solve the quadratic equation, but like, let's not do that, okay? So you end up getting x equals to 3.74 times 10 to the power of negative 4 moles per liter, and using that converted into number of moles, and then convert it into grams. Okay. So yeah, using IC table, this question can be like simplified a lot. Okay. Okay, question 15. Describe the changes that occur in both bonding and entropy when the potassium chloride is dissolved in water. Support your answer with the label diagrams. Okay. So potassium dissolves in water and forms an ionic bond. It attracts the negative charged oxygen atom, while chloride attracts the other side of the water molecules, which is hydrogen right there. Okay. So potassium chloride is an ionic compound that is soluble in water in a polar molecule solvent, with hydrogen bonding capabilities. Okay. When dissolving, ionic bonds between ions and hydrogen bonds between the water and they are broken, and then entropy therefore increases. Okay, it's more disordered. Energy is released into the surroundings. As the ions are less like ordered now, right? So it's more entropy. Consequently, the partially negative charged oxygen in water attracts the potassium ion, and partially that is partially positive. The hydrogen that's attracted to the chloride. Okay, this establishes ionic dipole bond, so this step decreases entropy. Okay, and then the overall effect. Right, you have to consider both entropy changes, whether the system increases entropy or not. Okay, usually a salt dissolution will be increasing entropy, but you have to consider those two steps individually, okay, to figure it out. Some salt actually dissolve and decrease in entropy. Okay, so it is kind of like describing delta H in terms of the process. It's like the same thing. Okay. Question 16. So the graph shows the concentration versus some saturated. Okay, the graph shows the concentration of silver and chromate ions, which can exist in saturated solution. Oh, you get this relationship. Okay. It's always nice to figure out a theoretical equation for this curve right here. Okay. So using the graph, calculate the molar solubility of silver chromate. So on this line, every point will be like a different equilibrium position, okay? Meaning that a different equilibrium concentration of that and that, giving you the same KSP. Okay, so if you were to be able to write down the chemical reaction, in this case, like say that's the Y, this is the X, okay? Then the KSP is actually equals to AG will be squared, so X squared times by Y, and KSP is a constant, and then you can say a Y is actually like a constant. I'm gonna call it K divided by X squared. Okay, and this relationship will be satisfying this function right here. Okay. So it's nice to always have some like quantitative, like sort of mathematical thing, mathematical tool in your mind to answer these questions. It's really handy and makes you more confident answering these questions. You know what it is. Using the graph, calculate the molar solubility of silver chromate in pure water. So write down the chemical reaction first, KSP. Okay. I mean, you just pick a point because every point it will be like a feasible equilibrium position. Yeah. Yeah, and be very careful about this, like the label of the graph. Like, it gives you negative 10 to the power negative 4. It's very easy to omit them and then end up getting the wrong value. Okay, so you first of all use whatever point on this graph, choose like a more convenient one. So I've chosen a one that's like cutting through like a grid. Okay, and then another one that's like better to use. I don't really see that, but yeah, try to pick the. Okay, I think this one. Yeah, but it's kind of weird. So just pick one and calculate equilibrium constant. Use that equilibrium constant. Assume x. Solve for x will be your solubility. Okay. Let me know if you guys any question. Question 17 is 100 ml of saturated solution of calcium hydroxide. It is at 25 degrees Celsius and it contains 0.173 grams of calcium hydroxide. Assume there's no precipitate establishment. Question A says calculate the solubility product of the salt. That means this saturated solution and no precipitate. That means 0.17 3 grams of the salt have completely dissolved. So just calculate the molar solubility, and then use that number to like get your KSP. And be very careful that the hydroxide is molar ratio, so you want to times this by 2, right? Like what I said here. Okay. Sorry, I'm a bit sick today. Okay. Question B. Explain why the undissolved solid is not included in the expression of the solubility. It doesn't have any concentration. Okay. Yeah, unfortunately, okay. All right, that's kind of disrespectful, but chemistry does have some like original stuff. Like we've seen in year 11. For some political reason, I don't think. Okay, let's just go through the question. Right, so Aboriginal and Torres Strait Islander people, they have been using technique from chemistry to remove toxic substance from food for a very long time. Yeah, yeah, they did. Outline a technique that is used by indigenous people to remove a specific toxin from food, which in the syllabus they tell us it's psychosin, and then it's kind of like one of the toxic substance in their food. It's called cycad, right? So it's kind of fruit, a tropical. It's like a tropical fruit. Okay, uh, right. And then the indigenous people, they learn to detoxify it with several different methods. Okay, and then in year 11 we learned the thermal decomposition. Now we use something, another technique called leaching. It's basically they soak the fruit in running water, in which it satisfies the requirement for an open system, right? So water is like running away, and then normally cyclosen is like really like not water soluble. Like it's very doesn't want to dissolve in water, ion organic compound. Okay, but if you put it in open system, although it doesn't want to dissolve, always forms a very like not favor dynamic equilibrium. But since you have an open system, so you just end up with a static equilibrium. So it just keeps dissolving, although happening very slowly, but it keeps happening, right? Dynamic equilibrium is never established because you have open system, and you will just eventually you have decreased the concentration of the cyclosin to like the safe to eat level. Okay, and then you can just consume it. Okay, so that's the idea. Pretty much you just soak the fruit in water for some times, and then you can eat it. Okay. Yeah. So guys, answering this type of question in the HSC, or it never came up in HSC, but like if you did or in your assignment, make sure to relate to the chemistry. Okay, in this case, would be the open system, and then the dynamic equilibrium being never has been established. Question B: explain how temperature can be used to improve the removal process that you have identified in part A. Right, the dissolution process will be exothermic, right? This will be like from the notes I send you. Um, so that at higher temperature, like just use LCP. It's pretty straightforward. Okay. So yeah, you just wanna heat the water up. Like if the water is hotter, you can dissolve better. Question 19. So lead sulfide is used as a white pigment. Okay. Its solubility in water is this much and this much in per 100 ml. Okay. Reaction simple as that. Calculate the solubility product. Okay. So given that per 100 ml you get that, so just use this number, convert it into molar solubility, moles per liter. Okay, that's what I did here. Since they're the same stoichiometric ratio, just get the same concentration, times it together, get the KSP value straight forward. Okay, part C, a few drops of concentrated that is added, and then I think you get a common ion effect. Okay, so using the Charlie principle, predict what will happen, right? So adding that increases the concentration of that, this causes the common ion effect. By the Charlie's principle, the equilibrium would shift to counter initial change despite this definition, as I get 1 mark from that. And answering the question, in this case, solution equilibrium shifts to the left, reducing the solubility. That's another mark, getting 2 marks. Okay. So at this point, you should be very familiar with how to use LCP. Okay, it's quite easy. How many questions did I write for this? Actually, a lot. Okay, 13.3 grams of potassium iodide is placed in 100 ml of 0.11 moles per liter of silver nitrate solution at 25 degrees Celsius. Assume constant temperature for this reaction. Right, so that's the equation. Quantitatively show that the precipitate is formed. Whenever we're being asked to show whether a precipitate is formed, equilibrium quotient is your way out. Okay, so calculate the molar solubility of iodine and silver, given that if it dissolves, and then calculate the equilibrium quotient, and then compare with the KSP value on the formula sheet. End up finding that it's actually very much larger, so precipitate does form. Okay. So question 20. Refer back to question 20. Let's calculate. So it's like a continuation of what you put. Let's calculate the mass of precipitate formed. Okay. So we know that it's going to be a precipitate. Okay. But what's going to be the mass? Guys, this question, if you think about it, it's actually pretty hard. And HEC chemistry is hard and because they have a lot of difficult calculation on those solubility and stuff. When we get towards the end of all the modules and we start doing revisions, you will see this is like it happens. So upon precipitation reaction, we know that the ion introduced will transfer into solid until some ions are dissolved partially. Okay. So like the solubility quotient at that point will be equals to KSP at equilibrium. Okay. So just get that, and then use the initial like the concentration above as your initial value, and then assume minus x, right? And then this time you actually need to solve the quadratic equation. Okay, because you know the KSP from equilibrium from the formula sheet. You get two values. So x being negative doesn't make sense. Okay, so x must be the positive value, and then you just convert the unit into grams. Okay. So yeah, really do check if you got the right answer for many of these calculation questions. Okay. Right. So these questions are not very difficult. From over the years, I've discovered that HSC question actually is like I've had more questions that's like more difficult than these. So I will try to find some of these questions, and then you will see them in the exam, or you will see them in the future. Okay. Right. But if you had no problem with doing these questions, you should be like relatively fine. Okay. Right, so this is it for the homework talk homework 4. So like enjoy chemistry. I'll see you module 6.